Hello.
Hi.
Can you I'm gonna pronounce your name, so I'm gonna announce you like really quick, just like two sentences.
Uh,
And then we can kind of get going.
yes,
So
sounds
it's
good.
Maryam Berijanian.
Yes.
Okay, perfect. Just let people come in really quick. Okay, I can kind of go ahead and start. All right. So, hi everybody. Welcome to the continuation of our 2025 to spring 2025, excuse me, seminar program. I'm Nikita Angarski. I'm part of the master student researchers that is volunteering to kind of run the AV here. So I'm going to be really quick with the introduction since we have only about half an hour. So we are really, really, really pleased to have with us today Maryam Berijanian, who is a researcher at Michigan State, focusing on AI, engineering, and science, or intersection of computational and social. So she's going to be talking about neural networks, how to extract valuable information from LLMs, and just tell us about the exciting research she's doing. So, without further ado, I'll just kind of take it over to you and mute myself so you can start your presentation, Miriam. Thank you.
Okay. Thank you so much for the nice introduction. Um, I want to share my screen. Um, Now. Okay, I'm not used to Teams. Uh, how can I?
It should be near the microphone and camera, but yeah, let me know if you can share. You should be able to, I think.
Oh, that is so not nice. It doesn't work. So window. Okay. Okay, I should give it permission. Um, yes. I'm so sorry.
No worries. Yeah, I had trouble with Teams as well when I first started here because it's Georgia Tech works on Teams, I guess.
I just don't know how to add teams to this list. Okay, it must work now. Oh, come on. So when you click on share, then do you click on window or anything else?
On the screen or on the window, so it should give you the option to select the screen. And then one should be, yeah, so I have, it depends if you how many screens you have running. And then in the window, it just whatever apps you have running, then you can choose from the windows you have on.
Oh, that is so embarrassing. Can I maybe send you my slides?
Yeah, yeah, sure. I will, let's see.
Mm.
Yeah. So, if none of it works, please just send to that email and then I can probably present it.
Okay, then what is your email address?
I sent it in the chat. Chat.
I can't even see the chat. I don't know what's
Oh, let me
happening.
see. That's probably, well, I can just put it in the chat anyway.
But I should have your email, I guess. Nikita. Okay, yeah, I see it now. Oof. I'm so sorry.
No worries.
I usually use Zoom, and it's first time actually. You should have received my email. Did you receive it?
No email yet. Maybe I might have went to, because it's external. Uh, Here it is. Okay, got it. Okay, there it is. And we can open in PowerPoint. Present. Yep, okay. And
Right.
there it
I
is.
apologize for the delay. I'm so sorry. So I want to talk about a paper from last November in a workshop of EM&NLP conference, which is about natural language processing. And here's the name of my colleagues. I just included the link. And in the next slide, we can have an introduction. So in the field of social science, we have complex social ecological systems that need to be modeled so that we can do predictions. For example, consider this sentence. Some fishermen describe the establishment of large numbers of blue mussels on the turbine structures. So we can see this as some kind of a causal relationship, meaning that in this sentence, turbine structures are somehow supporting blue mussels. So we can say turbine structures increase blue mussels. So this is the way we want to show a causal relationship. And then in the next slide, we see like an example of a complex model of a system that is about conflict and food system dynamics in Nigeria. For example, you can see like in the center, we have banditry, and the blue arrows mean an increasing relationship. For example, banditry increases bandit networks. And the red ones are decreasing relationship. Um, and yeah, and these kinds of graphs are useful to simulate and do predictions. For example, if stakeholders increase one of these, then what will happen to the whole system? Stuff like that. So having these kinds of graph is really helpful in this field. And then the goal is to extract them from scientific papers. In the next slide, yeah, this is again a very simpler example. So the goal is to extract these graphs named fuzzy cognitive maps, FCMs, from scientific texts. And the problem is that extracting them is really difficult because we have a huge amount of texts. So we wanted to use large language models to automate this task. In the next slide, please. So at left, we can see, for example, fisheries stakeholders. They can be some sort of like a source of information. For example, we do interviews with them, or we have access to scientific papers or public comments and so on. And all of them together will be a source of information for us and in the form of text. So we can use large language models to extract these kinds of graphs. And also we can like domain experts can do also this task. And then what the domain expert produce is the ground truth. And we can then compare the LLM's output with the ground truth and use it as a feedback to fine tune them and iterate to improve them. The problem in this process is actually comparing the output of LLMs with the ones generated by humans. And comparing needs specific metrics for this domain. And there are not so many metrics for this specific application. And this was the problem that we had. So next, please. So in this work, we wanted to address this problem. And in order to have a good metric, we have to be able to address high expressiveness and partial correctness. High expressiveness means that these graphs can be expressed in multiple ways, and partial correctness, let me explain it in the next slide. It's better, maybe. So this is, again, the same example from before. So turbine structures increase glue muscles. And assume that we use an LLM to do this prediction, to extract this information. And if the entities are correct, like turbine structures and blue muscles, but just instead of increase, we have decrease. Or for example, the last one, instead of turbine structure, we have turbines. Or instead of blue muscles, we have muscles. These are still correct, but not exactly the same as the ground truth. And if we use a metric like F1 score, it is too harsh for this, for evaluating this example, because it doesn't matter if it's partially correct or completely incorrect. They all would be treated the same. So we wanted to come up with a new metric to address this problem. In the next slide, so the objective is to fine-tune large language models to extract FCMs, and then how to evaluate them. So before I dive deeper, I should talk about ELO algorithm. ELO algorithm is something that's used for calculating a ranking between players in two-player games like chess. And when two people play against each other, the winner gets like 1 score, the loser gets 0, and so on. And then after the whole tournament, we have all these scores, and we can calculate a ranking. In the next slide, these are the formulas that are used with ELO algorithm. So assume that A and B are two players, and we want to predict which one wins. So EA and EB are the expected result that are either 0 or 1 for the win and lose. And then RA and RB are their current rankings in the system. And based on their current rankings, we calculate an expected result. And then at the bottom, we have the formula for calculating the new rankings based on the actual results. So SA and SB are the actual outcomes, and based on the current rankings and the actual outcomes, we can calculate their new rankings and their update them. So after the tournament, we end up having a ranking of all players. Next, please. So we use the same idea for evaluating metrics. So we use ELO as a meta metric. And these are the steps. I will explain them in more details. The first step is sample selection and annotation. Then we have pairwise comparison, which acts as like a chess match. And then we do ELO ranking. And then on the other hand, we use some metrics, including ours, to calculate scores for the annotated samples. And we obtain another ranking. And then we compare the ranking obtained by ELO and the ranking obtained by metrics to see how they correlate. Next, please. So the first step is annotation. In this work, we created our own data set. We had 300 short text passages, and the annotation was done in a UI like this. So we have a sentence, and we should mark the source, which is like the first entity, then the target, the second entity, and then direction is either increase or decrease. So it's like that example of turbine increases blue muscles. It's similar here. And so annotations are in the form of source, target, direction tuples. And then next, we also used some large language models to do annotations. In addition to human participants, we used Llama 2, Llama 3, and Mistral models in these two ways with instruction fine-tuning and few-shot learning. So with these models, we also generated those annotations, the same as like the humans. And then next, please. And this is an example of a prompt that we used for instruction fine-tuning. So for example, we give it this instruction, like given the input sentence, identify all the triplets of entities and the relationship between them and so on. And we give it the input sentence and the expected output, and we gave it like 3 of them, so 3-shot learning and also 5-shot learning. And in the next slide, yeah, this is then the tournament. So we have a pairwise comparison between annotations. So each user can see 2 of these annotations for the same text. And the user doesn't know which one is generated by whom, which one was generated by an LLM, or they didn't know which is which. But they just have to choose which of these 2 annotations is a better annotation for this text. So it is similar to that chess match that we had before. And in order to unify them, we had a set of guidelines for them. For example, if you see like an entity is mentioned like not complete, then you should prefer a complete entity over an incomplete entity, stuff like that, so that all participants had similar responses. And next, please. And then the next step would be calculating the ELO scores after the pairwise comparisons. So for each of the passages, we were able to calculate this ELO score. I also wanted to show you some side results, like reliability of results. So according to our analysis, all of the participants agreed on 50% of data, and the other half of the data had 3 parts. So 20% of the data was agreed upon by 85% of participants. And for example, 10% of, like 57% of participants agreed on 10% of the data, and so on. It means that when we calculate the sum of like 50%, 20%, and again 20%, it's 90%. So 90% of participants, 90% of the data received agreement from 71% of participants. And also each person had about 90% self-consistency. So it means that so the self-consistency is good, like 90%, and there was some kind of difference between the participants, and it was expected. And it's actually a good thing because we want to consider opinions of different people so that we have a democratic way of choosing the winner of the tournament, actually. So it was just a side analysis. But then in the next slide, these are 4 metrics: blue, rouge, meteor, and blurt. These are 4 metrics that we use. And I intentionally have metrics here, but metric has a special meaning in math, so it should be a distance between 2 things. But these metrics. These are not metrics, actually. These are similarity measures, because for a metric, a lower amount is better, meaning that a lower distance is better. But these are similarity measures, meaning that a higher amount is better. Yeah, but when I say metric in this work, I mean similarity measure, actually. Okay, next. So the way that we defined our metrics was similar to F1 score, but we added an additional term of partial positive. So PP is partial positive that we added to the usual F1 score. And the reason was that, like I said at the beginning, that we want to account for partially correct examples. And next slide, please. And since I don't have a lot of time left, this is how we count the true positives, partial positives, and so on. So the gist of it is basically we use those 4 metrics, blue, rouge, and so on, to calculate the similarity between an extracted graph and a ground truth graph. And then if it is higher than a specific threshold, we accept it as a partial positive or true positive. If it's lower than a threshold, it is false positive or false negative. And this is what we did. And then we named them blue E, rouge E, and so on, because E stands for edge. So we consider the edges of the FCMs. So these were how we defined our metrics. And then in the next slide. Remember that ELO tournament? So we took the winner of each tournament as the ground truth. So the one that was ranked 1 was the ground truth, and we compared all the other annotations with that. And we used those metrics to calculate their score. And then based on those score, we could rank them. And on the other hand, that ELO tournament also gives us some ranking between the annotations. And then we can compare the rankings based on ELO, which were chosen by humans. We can compare them with the rankings based on the metrics and obtain the correlation between them. And in the next slide, you can see correlation between them. Like F1 score here is the usual vanilla F1 score. It has the lowest correlation with human judgment. And then the orange ones are metrics without considering partial positives. But then when we add those partial positive terms, we obtain the blue ones with higher correlation. So it means that with these metrics that we defined, they are more similar to human opinion. And also this ELO algorithm could be a method for comparing metrics with each other, like a meta-metric. Yes, and and the best one was Bluey. It has the highest correlation with human judgment. And then we use this Bluey in the next slide. We used Bluey to evaluate the 3 LLMs that we had. In our study, Mistral was the best, and then Llama 2, and then Llama 3. And here we can see another interesting thing is that before fine-tuning, Llama 2 was the worst model, but after fine-tuning, it changed. It was Llama 3. And another thing to that is important is that even the best metric, Bluey, it was only 40% in correlation with human judgment. In next slide, please. So this metric, even the best one, had only 40% correlation, which means that we still need even better metrics that align more with human judgment. But this study was at least showing how we can evaluate these metrics and how we can define a metric that correlates better with human judgment. And yeah, I don't have a lot of time left. I'm so sorry. And for future, maybe we can parameterize those true positives and partial positives so that we can do optimization, so that we can obtain a better metric. Yes, that was all. And my contact information is in the next slide. And I would love to connect with you if you want. Yeah, and the GitHub link is for this project. It has all the data sets and the codes that we had. Yeah, thank you for this opportunity.
Yeah, this is very cool. We actually have in our research team people who are doing similar work with legal language. So I'm pretty sure this is going to be super interesting for them to look at and possibly reach out. Otherwise, anybody who's viewing this and has access to the meeting, we have your contact info, your LinkedIn in the bio. But yeah, just and this is going to be on the recording, so we can definitely um we could definitely kind of connect with you through there as well. I do have one question from one of our audience. Do you think testing with other LLM models apart from Llama and Mistral will create different results? And I noticed you had a few there, but in the future, are you planning to extend this research to any other LLM models?
Yeah, we can do that. The focus wasn't actually but on these like which LLM is the best. The focus was which metric is the best. But it is interesting to see, for example, with the new models like DeepSeek that weren't available at that time. It's interesting to see how they perform. But I just wanted to remind you that the focus was comparing the metrics, not the LLMs. Yeah.
Right. And then yeah, so personally as well, there is a question that I had. So yeah, so in the do you expect, so you found that on average Bluey scored kind of the highest. Is the so to that question, are you going to plan to explore kind of even other metrics, or are you like what other metrics like are there, I guess, to compare how well this like LLM synthesizes the information, and like how does that scale with, I guess, complexity of the question? So in the examples you gave, you were mostly doing like increase or decrease, that kind of synthesization. But what if there are any kind of that you have in mind, what are kind of more complex um, questions you can kind of pose to synthesize like an article or sentence? And do you expect Bluey to perform as well, worse, or or better?
Okay. One thing is that there aren't so many metrics that we can use, and we have to come up with our own for this very specific application. And like these metrics, like Bluey, Meteor, and so on, I think they were initially introduced for summarization tasks, even not for this graph comparison tasks. So actually, there wasn't any metric that we could use. This was like the closest ones that we could use. And so when we want to do, like when we want to continue this research, we have to come up with our own. And one way is to, as I said, to parameterize these definition of partial positive, true positive, and so on, so that we can do optimization and improve these metrics. Another one is to automating those ELO experiments. So when we wanted to compare, like when we wanted to do pairwise comparisons, all of them were done by humans, which adds efforts. And it's nice to like it would be nice to automate this by using like agents to do these comparisons for us. And when we can do that, then it can be done faster, and it means that we can repeat it and iterate it until like we can iteratively obtain a better metric. So we try a metric, do the experiment, and then based on the feedback, we change the metric and so on. So that is another idea. Um, did I answer your question?
Yeah, yeah, I do like the idea of I guess grading LLMs at scale with other LLMs. That sounds interesting to me. So that's probably that sounds like a promising future. So that's good. Um so we are just about running on time. Let's see if I have any questions, any more questions. I think for now, yeah, I think we can kind of close this out. If you have anything else to say, let me I want to share your contact page again, just as you close out. So let's see. Yep.
And the project about legal language, is it the one with Professor Charlotte Alexander?
Correct. Yep, that's the one.
I am aware of this because we have meetings every week with students working on this. Um, yes.
Yep, so there I'm not too familiar with it. I know that it's being like done in conjunction with legal offices and I believe the Dominican Republic. So yeah, so you guys can obviously have a lot to talk about. But yeah, so please reach out if you have any questions or would like to collaborate with Mariam here. That's a really nice QR code. I'm gonna steal that idea probably for later. But anywhere else, and yeah, so LinkedIn, take a look at the GitHub. And yeah, so thank you so much for presenting. And we look forward to keeping in touch. This recording will also be on the Hag YouTube. So it could be like shareable and I can send you if you like the recording afterwards. So yeah, thank you so much, Mariam.
I thank you for the opportunity to present my research, and I would love for you to connect with me if you want and to collaborate. Yeah, thank you.
Very cool. Thank you so much.
Thank you.
All right. Have a good one.
Thank you, you too.
Bye.